Hello, my name is Jessica Jauka. My theme is Control Lighting Lead with PWM. Definition: the light-emitting LED has quickly become the preferred choice for many lighting applications. The improvements in efficiency and brightness made by LED manufacturers mean that there are some other equivalent options for application ranging from automotive headlights to factory and warehouse lighting. One important advance of LED over other options is its control capability. Although this requires the use of electronic circuits to take full advantage of the technology and not introduce problems, such as flicker or overheating.
Hey, this is Jesse with Create This. So today I'd like to talk about two different ways to control LED brightness. So LED dimming, basically. First, I'll show you the most straightforward way. So the most straightforward way to dim an LED is to reduce the current going to the LED, or possibly the voltage, or both. So first, here's my LED strip. This is I think these are 50/50 SMD LEDs. I actually bought these at Radio Shack. They come in a long strip. This is actually the kind of packaging that they come in. It's supposed to be like waterproof or something, I don't know. They were fairly expensive. I think I bought them maybe a year or two ago, and they were fairly expensive at the time. They've come down in price, if you know where to get them, quite a bit. So I'm going to provide a link for all of this stuff that I show here today down in the description, and if you want to buy it on Amazon, it won't cost you a dime, but if you click the link and buy it through me, I get a little kickback and it helps me support the channel. So, and plus, you'll get these quite a bit cheaper than I bought them. I think they're going for like $9 or something these days, so I think I bought mine for like 30, so, Good deal there. Anyway, I'm not going to go over how I made this panel, but basically, I've got two leads here for positive and negative, and I've just got them joined in series here. Okay, and then this last one is not joined to anything, and that's just the way the circuit works. It flows all the way through and then back to the negative lead there. So anyway. Let me show you that, let me prove, this is a 9-volt battery here. Let me prove to you that this works first, and then we'll dim it, okay? So I'm just gonna connect my alligator clips here on the positive end of the LED and the positive end of the battery. Oh, got the insulation there. Positive end of the battery, and negative end of the LED, and negative end of the battery. Okay, and then I've got a switch right here. Just turn it on, instantly bright, right? But what if we'd like some control over how bright it is? So the simplest thing that I could come up with for this, and there are, like I said, there are two ways to do this, but the easiest and most straightforward way is to simply add a resistor. And in this case, this is a potentiometer, so it's a variable resistor. It's got this knob right here, and as we turn the knob, we can vary the brightness. So I'll show how that circuit works next. So we just attach the positive lead to the battery here, and the negative lead, other positive lead to the middle terminal on the potentiometer. I don't remember why it's got 3 terminals at the moment. Can probably look that up later. Attach that to the positive lead on the LED. Negative lead on the battery to the negative lead on the LED. All right, so now when I turn it on, you can barely see that it comes on just ever so slightly. And as I increase the voltage here by the voltage and the current by twisting this potentiometer, you can see that I can vary the brightness. Now, just to give you a little bit of backstory, the reason why I built this thing is because I wanted, I had these 3D printed lithophanes, and they're basically, you know, like an image printed in height map, right? And so what you can do with this is you can put it over this backlight, and you can raise and lower the brightness, and the image becomes clear. And the further you are away, the better the diffraction is, so it's a little easier to see. There we go. So that's maybe an inch away from the back of the LEDs, so I could put that in a box, and you know, that would look pretty awesome, right? Now, what's going on here in this circuit? This is a resistor. I already mentioned that. This is the battery, and that's the LED, right? What happens is when you put a resistor into a circuit, it modifies the amount of current going to these LEDs, and it also modifies the voltage. Now, I can show that, I can prove that to you with a multimeter. You should always have a multimeter if you don't have one. This is kind of an expensive model. I have two of these, not two of the, this is a Fluke 87. I've got a Fluke 87 and I've got a X-Tech. I think it's a 430, X-Tech 430. The X-Tech is much cheaper. They both do pretty much the same thing. I think the Fluke 87 has some additional features, and it's probably easier to use. So I'll provide a link to both of these in the description. But today we're going to be using the Fluke 87 because I just bought it and I want to play with it. Okay, so let's see. First thing we should do is we should take a look at the voltage. That'll be the most interesting thing for me right now. So to do that, I'm going to measure the voltage at these two leads because this is the LED. This is where the LED is seeing the voltage after the resistor because it flows through the circuit, flows through the resistor. So I'm going to measure it right there. So first thing I'm going to do is I'm going to attach my negative lead from the multimeter. All right. And second thing I'm going to do is I'm going to attach my positive lead from the multimeter. Okay. And you can see that it's already registering 7 volts. And then as I vary the potentiometer and I increase the voltage, look at that, 7.2, and you can see the LEDs are getting a little brighter. 8.6, and that's about where it tops out at, 8.6. So pretty interesting. Now, what's also happening is
application. Arduino has an integrated analog digital converter by which we can receive voltage between 0V and 5V to be translated into numbers between 0 and 123. However, we do not have an analog digital converter which to send voltage signals continuous other than 5V, as for example, controlling the intensity of an leaf. To solve the above problem is that the pins that can see signals which pulse with modulation PWM are used. To do this, we need to connect and lead to one of the pins that allow PWM signals as output.
Hello everyone! Today we are going to talk about PWM and what you can do with it. PWM stands for Pulse Width Modulation, and it consists consists of producing a square wave which you can control the up or high time. In a PWM signal, the minimum and maximum voltage are the values that limit the wave's oscillation. The space between them is called amplitude. A cycle is the interval of the wave where you can find one full repetition. The time a cycle takes to finish is called period, and the frequency is 1 over period, which gives you how many cycles are in a time unit, usually a second. A very important concept in PWM is the duty cycle. The duty cycle represents how much of the period in which the signal is high. In our wave, the signal here is high, and here is low. To calculate the duty cycle, you need to know how much of the period the signal is high. Let us set our high time as 6 milliseconds, our downtime as 4 milliseconds, and our period as 10. Now, let's use a simple rule to calculate the percentage of the period in which the signal is high. 6 relates to 10 the same way as our variable in percentage relates to 100%. If you solve this, you'll see that you get 60%, meaning that the signal is high 60% of the time. Let's imagine a PWM signal that oscillates between 0 and 5 volts. Let's say this signal has a duty cycle of 50%. Something interesting will happen to the output voltage. Instead of being 5 volts as expected, it will now be 2.5 volts. Simply putting it, this is because in a PWM signal you multiply the max voltage by the duty cycle. This is the formula. By applying this to our situation, you will see we will reach 2.5 volts. Let's see what happens to the different components of the wave when I increase the duty cycle. As you can see, when I increase the duty cycle, the output voltage also increases. And when I decrease the duty cycle, the output voltage also decreases. Keep in mind that the output voltage can only oscillate between the minimum and the maximum of the PWM signal. Now, let me show you this example in real life. We are going to use an Arduino, a breadboard, a LED, and any resistor between 1K and 300 ohm. If you look closely at an Arduino, you'll see some pins have a tilde symbol. This means these ports can output a PWM signal. Now let us set up a simple LED configuration. Connect the Arduino power to the breadboard. Next, place the LED on the breadboard and also the resistor between the LED and the ground. Now, simply connect a cable between any port that can handle a PWM signal. Last but not least, we have to create a program to control the PWM port. Assign the port that you connected your LED into a variable. I will call it PWM. Now, this byte variable will represent the PWM value. The reason I chose a byte variable is because the PWM in the Arduino has a resolution of 8 bits. So you have 8 bits or a byte to encode the value of your duty cycle. 0 means 0% and 225 means 100%. In order to control the PWM ports in an Arduino, you use the analog write function. The first parameter is the number of the pin which you want to control, and the second is the value of the duty cycle ranging from 0 to 225. We want the PWM value to slowly increase with time. For that, we will increment the variable each time the program goes through the loop. In order for this process to be slow, we will have to introduce a little delay. 20 milliseconds should do. Now, we don't have to reset the byte value, because when it reaches its maximum, or 225, it becomes 0 again. At your left, you are looking at my old oscilloscope showing the PWM signal. At your right, the LED becomes brighter the higher the duty cycle, and it becomes less bright the lower the duty cycle. Thank you for watching, and I will see you in the next video.
Pros and cons. Pros: vary the speed of a motor, vary the emission intensity of lead, transmit the degrees of rotation of a servo. Cons: relatively more expensive, blinking in peripheral vision is perceived if the driver is below a frequency of 100 Hz. Stroboscopic effect evident in fast-moving environments when the drive frequency is low. Electromagnetic interference means problems due to drop and current peaks in the PWM regulation. Performance problems arise when the drive moves away from the light source.
Pulse width modulation, or PWM, is a term you hear a lot of if you're interested in controlling power output using a microcontroller. It has many applications. One of the most popular amongst hobbyists is controlling the brightness of LEDs. In this tutorial, we will cover the basic principles behind PWM and how it can be used for LED brightness control, including fading out LEDs rather than just turning them on and off. To control the brightness of an LED, you can vary the power which is sent to the LED. The more power the LED receives, the brighter it is. The less power, the dimmer it is. However, microcontrollers are digital, meaning they only have two power states, on and off. PWM provides the ability to simulate varying levels of power by oscillating the output from the microcontroller. If over a short duration of time we turn the LED on for 50% and off for 50%, the LED will appear half as bright, since the total light output over the time duration is only half as much as if it was 100% on. The pulsing width is the important factor here. By varying or modulating the pulsing width, we can effectively control the light output from the LED, hence the term PWM, or pulse width modulation. When using PWM, it's important to consider how slowly we can flash the LED so the viewer does not see the oscillation. The eye's inability to see rapid oscillations of light is caused by our eye's persistence of vision, which means we see the light is on for a short duration even after it's been turned off. This technique is how televisions display a moving picture, which is actually made up of a number of different still frames displayed one after another. The minimum speed of an oscillating LED which can be seen by the human eye varies from person to person. However, for the purpose of this tutorial, we will use a minimum speed of 50 Hz, or 50 times a second, which is the same speed as used by European televisions. When using PWM, there are certain terms which you will come across again and again. The most important is duty cycle. The duty cycle refers to the total amount of time a pulse is on over the duration of the whole cycle. So at 50% brightness, the duty cycle of the LED is 50%. The cycle itself is measured, usually, in hertz, which gives us the cycles per second. So at 50 hertz, our cycle is 1 second divided by 50 cycles, which is 0.02 seconds per cycle. Since we are using such small time measurements, it's more useful to use microseconds. There are a million microseconds in a second. This gives us a cycle duration of 20,000 microseconds, which is 50 cycles per second, or 50 hertz. During the 20,000 microseconds, we have to turn the LED either on or off depending on the required duty cycle. So for example, a 75% duty cycle requires the pulse to be on for 15,000 microseconds and then off for 5,000 microseconds. The accuracy with which we can control the duty cycle is known as the PWM resolution. The higher our PWM resolution is, the more levels of brightness we can display. However, since the duty cycle is fixed at 50 Hz, more resolution requires finer timing from the microcontroller. The faster the microcontroller, the smaller durations it can time. Another limiting factor is the code execution. The microcontroller must not only time the interrupt which causes the pulse generation, but also run the code which controls the LED output, which must complete before the next interrupt is called. In addition, you probably want your microcontroller to be performing tasks other than LED PWM brightness control, so there has to be some spare execution time between interrupts to do all of the other more general processing tasks. With PWM control of LEDs, the primary advantage of higher resolutions is that it results in a smaller difference between brightness levels from the LED. For example, if our cycle is 20,000 microseconds and our resolution is only 10,000 microseconds, the difference between on and the lowest possible brightness will be 50% of the total possible brightness from the LED. At a resolution of 2,000 microseconds, the difference would be 10%, and so on. The higher the resolution, the more timing accuracy and processing overhead.
Insert application in Ecuador. Thanks to the combination of support for network-based control, the ability to connect sensors, and use advanced state machine strategies to manage lead output, the SDLUX Ranger of devices provides a very suitable basis for advanced lighting system.
This video shows how to control the brightness of an LED using pulse width modulation. You should already be comfortable with controlling an LED and be able to use for loops in Python. In digital logic, a pin can only be in one of two states. Either it can be off, which is represented by a 0, or it can be on, which is represented by a 1. These correspond to two different voltage values. In the case of the Raspberry Pi, off is 0 volts and on is 3.3 volts. It doesn't matter what time we look at the signal, as it always remains the same. This makes it easy to turn things on and off, but it's harder to get something in between. For instance, an LED switched on at only half its normal brightness. One solution is to use pulse width modulation. In pulse width modulation, a pin will turn on and off at a particular frequency. Here the wave goes on and off every second, which gives a frequency of 1 Hz. A wave which goes on and off every 2 seconds would flash slower and have a lower frequency of 0.5 Hz. I've set up 4 LEDs to show the effects of changing frequency. To see this better, I'll turn off the lights. The top pin has been set up as an ordinary output, so as to compare with the 3 pulse width modulated LEDs. The third and fourth pin are at 1 Hz and 0.5 Hz respectively, which is low enough that we can see them flashing. The second LED is set at 100 Hz, which means it's turning off and on 100 times a second. That's of course faster than our eyes can notice. But notice that the second pin is effectively half as bright as the top LED. This is because it's on for only half as much time. So if we flash an LED fast enough, we can get an LED which appears half as bright. But what if we want an LED to be at 75% brightness? For this, we need to change the duty cycle, which is a measure of how often the pin is high. Notice that both waves have the same wavelength, but that the bottom wave has a higher duty cycle. Specifically, the top wave has a duty cycle of 50%, since it's high 50% of the time. And likewise, the bottom wave has a duty cycle of 75%, as it's high 75% of the time. So if we want to gently dim or light an LED, we simply need to gradually change the duty cycle. Here's the Python code you will need to know for pulse width modulation. The output pin is set up as usual. Channel represents the pin that will be used for the output. Instead of setting the pin high or low, we instead create an instance variable p. We need to indicate which channel we are setting up for pulse width modulation and at what frequency. Keep in mind, just like a typical variable, you can change p to any variable name that you like. To start an instance of pulse width modulation, we use .start with the duty cycle in brackets. To dim or brighten an LED, we will need to continually change the duty cycle, which we can do using this method. Also, if we want to change the frequency, we can do so with this method. Lastly, we can stop the pulse width modulation using .stop. In this program, we'll set up one LED to continually dim and light. First, import the necessary modules and set mode for pin numbering. As we're only using one LED, we need only set up one GPIO pin for output. We then make an instance of pulse width modulation for pin 7 at a frequency of 50 Hz, high enough that we won't be able to see it blinking. This has only set up the pin, so we need to start the pulse width modulation with the start method. In this case with a duty cycle of 0. Effectively, the LED will start off. As we'll be using a continuous loop, we should use a try except block. This gives us a safe way to end the program by pressing Ctrl-C, which gives a keyboard interrupt which would cause an exit from the try except block. Then the pulse modulation would stop, and the GPIO pins would be reset. In the while loop, I've put 2 for loops. The top one makes the LED brighter, and the bottom one dims the LED. Each go through 100 steps. In the first case from 0 up to 99, and in the second case 100 down to 1. We need to put a sleep command in to make sure that the LEDs are not changing state too quickly. And there we have it.
Conclusion. The output range of an analog signal in Arduino varies from 0 to 255. A specific voltage is obtained by entering a value between 0 signal equals 0 B and 255 equals 5B. For example, a value of 2.5B is achieved by assigning 127 The signal taken to adapt into the PWM output signal must be transformed by a simple mathematical operation.
Hello again and welcome to the Smart Microcontroller channel. And if you're a new viewer, thanks for deciding to watch this video. I hope you enjoy it. In today's video, we look at using the pulse width modulator function of a microcontroller. The Arduino platform makes this function really easy to use by using the analog write function with an added variable. To demonstrate what the pulse width modulator is used for, we connect up an LED and vary its brightness using this function. It's quite simple to get going, so let's start building. What is pulse width modulation, you ask? Well, in simple terms, it is a signal technique where the width of a pulse is varied. The pulse is given a set frequency and the width of each pulse is varied according to what it is used for. In our tutorial, we will use the pulse to vary the brightness of an LED. The Arduino pulse width modulator function is set in the analog write command. The frequency is fixed at about 500 Hz, so we don't need to worry about this part. We just need to select the output pin to use and the pulse width that we want to output. We need to know that there are 256 levels of width to choose from, starting at 0 and going to 255, where 0 represents no pulse width and 255 represents 100% pulse width. This relates to no pulse with the LED will be off, and 100% pulse width, the LED will be fully at its brightest level. For the example we are demonstrating, we require the following components: an Arduino Uno, a white LED, which is rated at 3.3 volts, a 100 ohm resistor, connecting bits such as a breadboard and hookup wire. Looking at the schematic, this is how we will wire up the circuit. We use pin 3 as a pulse width modulator output that is connected to the LED through the resistor back to ground. It's very simple indeed. Okay, here is the code for the pulse width modulator brightness control for the LED. Now what we're going to do in this is we do a loop so that we start with a duty cycle of 0% and ramp it all the way up to 100%, and then it resets itself, and so we have an LED that goes bright, then off, then bright, then off again in a continuous cycle. Now we start here with pin 3. We set the integer output pin 3, and we set that to equal pin 3. And then we set the brightness, the initial brightness level at 0, which is a 0% duty cycle, so the LED will be completely turned off. And then here in the next line of code, we set the pin up as an output, so pin 3 is set up as an output. And now we get into the loop where we write our actual program. So we use the analog write function, and we set it up so that we're outputting to pin 3, and we're outputting the variable of whatever, the brightness variable, whatever that value is at the time. And it can be anywhere from 0 to 255, which is 0% duty cycle up to 100% duty cycle. So fully off to fully on. And then we introduce a short delay of 3 milliseconds between each variable write. And then we increment the brightness by 1. And then it loops again, starts at the beginning and keeps going. So it starts at 0 and keeps incrementing until it gets to 255. And then it resets itself again and then does 0 to 255 continuously. So what we'll do is we'll upload that to the Arduino Uno module. Just click on upload button. Takes a few seconds, and then within a few seconds it should start the loop itself. And let's have a look at the LED. Let's have a look at us controlling the LED brightness now. Now that the code is done, here we have the working prototype with the LED's brightness ramping up from fully off to fully on with a 3 millisecond delay between each level increment. Well, I hope this video was useful.
Thank you for your attention.